All right, so let's take a look. So we've got all this information here that they gave us. What are some things that might help me to do better in terms of making a prediction? What might help me to do better? What information might help you make a better prediction? All right, the height of the ball. When? Yeah. So if we knew the height before the video froze and after the video froze, that would definitely help me. Okay, so that would help me for sure. All right, so then if we look over at the next part, it says, all right, so we got several data points. Record the data that was before the video froze to estimate the height of the ball. And so the ones we had were 0, 2, 3, 3.5, 4, up to 4.99. Okay, and it gave me several heights there, 7, 11.16, and then we get into 14.56, 14.918, 14.992. Okay, so just looking at some values. We do that same thing for afterwards. 5.01, 5.1, 5.5, and so on until we get to 8, 10, and 14. Okay, and then we'd put in our values, 15.008, 15.078, 15.36. As we get farther away, at 10 we have 15, and at 14 we have 9.24. Okay, so those were the values that they gave us. All right, fill all those in. So question, do our answers in part A and B agree? What do you think tells us? Okay, what do you think is the height before the video froze, or what is it close to for A? What's our height getting close to? If we froze at 5 milliseconds and at 4.99, it's 14.992. What would you guess is probably the height? Yeah, I'd say it's probably 15. All right. One way we could write this is the limit as t approaches 5 from the left of h of t would equal 15. That's what we think it is, just based on the data. 14.992 is pretty close to 15. Okay. Likewise, if we do the same thing on part B, what do we think was the height of the ball at 5 milliseconds? All right, if we're looking at after that exact 5 milliseconds, what would you guess it is? 15, right? 15.01, 15.1. Gradually, they're getting going farther away from 15, but they do look at about 15 there at 5 milliseconds. So this one, limit as t approaches 5 from the right of the height is 15. So in part C, do our answers match? Yep. All right, they sure do. Okay, because this is a limit, we're getting closer and closer to a certain t value. We can say that it must have been at 15 feet after 5 milliseconds. Okay. And so if we're using limit notation, because it's true from both sides, as t approaches 5 of h of t, it would equal 15. Okay, so we're using that whole concept of a limit, looking at a table. So as x gets closer, or t gets closer to 5 from the left, our y values or our height values get closer to 15. Okay, as t gets closer to 5 from the right, so that's what the bottom table is, so we're coming into 5, the height's getting closer to 15. So that's that whole limiting concept. All right, so then they switch gears a little bit and they say, okay, here's an actual function for the height. Okay, so they give me a height function, negative 0.16 t squared plus 2.4 t plus 7. They ask you to graph it. And so it looks something like this. They've got some exact points on there. I can't read. Focus. Okay. And so that at 5. Well, I'm writing with a highlighter. That's not good. And so then at 5, we're at 15. And so it's looking something like this. All right, based on the data that we have. Okay, and so it asks you to trace the graph. All right, do you remember how to trace a graph? Put it in y equals, and then just hit trace. Okay, you put it, is that under, where's that at on your calculator? I can't remember. Let's jump over here and get mine open. Okay, so if I go to y equals and I put that equation in, negative 0.16x squared plus 2.4x plus 7, and I graph it. I'm not sure what I'll see. Ooh, let me zoom 6 it. Zoom 6. All right. Obviously, I need to see more of the top part and more of the right-hand side, so I'm going to adjust my window to make my x max. I'll make it 20, and I'm going to make my y max 20 and graph it. Okay, that looks better. Okay, and so if we hit trace, right, it will take you several places, but we can look as we get closer to, did I type it in right? Negative 0.16 t squared equals negative 0.16x squared plus 2.4x plus 7. Okay, all right. And we graph. We can trace that way. All right. So as we get closer to 5, right, we can watch those y values, and they get closer to 15. Likewise, if we come in from the right, same thing. All right. Now, I think it's interesting. All right. What's the value of the function at exactly 5? It's exactly 15. And I think that's part of what they wanted me to see. As we come in, as t increases toward 5, so that's coming in from the left, we're getting closer to 15. And then as we come in from the right, 15. So how could we have gotten the exact value at 5? We just plugged t equals 5 into the equation. Okay, so evaluating a limit from a table is just like evaluating one from a graph. Okay, the reason we might use a table is if we had, let's say, something, some crazy function, all right, where if we graphed it, we couldn't see the numbers like we could on some of the other graphs that I've pre-given you. Okay, so this is going to lead us to both things that we're going to talk about today. So when we evaluate limits from a table, okay, we're going to construct a table using small increments. From the right and from the left. Of the x value we're approaching. Okay. I want to show you what I mean by small increments. Okay, so let's say that we're trying to get to 5, right? So if I'm coming in from the left, I might use these values, 4.9, 4.99, 4.999, okay? So I want to use these small increments. What's happening as I get close to 5, all right, from the left, okay? Likewise, if I'm coming in from the right, I'm going to use incremental values like 5.001, 5.01, or 5.1, something like that. So we can see what we're getting close to. Now, one of the ways to do this, all right, and the easy way to do this is to put your table in ask mode. because we're going to always use the calculator to do this. And 9 times out of 10, when they're not going to ask me to construct that table. They're going to give me the table and ask me to look at it. Okay, but if we're going to do one here in a second where we're going to put our table in ask mode. And so the easiest way to do that, all right, is, let me think of the keystroke. Second window. Okay, second window. And your independent variable, you're going to put it in ask. Okay. And so what's going to happen is you're going to actually input the X value you want. It will give you the Y value you're looking for. All right. Just remember to take it back out of that if you ever want a full table. All right. So we're going to put our table in ask mode. So second window, the independent variable, we're going to switch to ask. Okay. I think it says automatic and then ask. Is that what it says? Okay. So we're going to do one here in just 1 second. I'm going to do an example and then, all right, like I said, they're going to give you the table. You'll rarely have to create it, but sometimes it helps. If you get to a limit and you're really stuck and it's calculator active, table's a nice way to look at it, okay? So it's just kind of a nice fallback. It's a way to double check yourself, which is also very good. Okay. All right, so let's look at this next example. All right, so we're going to use a graphing utility to confirm our result. We're looking at the limit as t approaches 5, so I'm going to actually put 5 in the middle of that table. Okay, so coming in from the left, my 4.999, 4.99, and 4.9. All right, and then from the right, 5.001, 5.01, and 5.1. All right, you can even do smaller increments than that. It's fine. All right, so what we're going to do is we're going to go to y equals, and we're going to actually put this function in. All right, so we want to be sure that we get the radical in the right place. We're using the fraction bar, all that good stuff. Okay. So if I go to y equals, and I'm not really going to be concerned about the graph because we're just going to look at the table. So I have alpha y equals, so I get a fraction, and then second x squared, x plus 4. Be sure you arrow out of the radical, and then do the minus 3. And then on the bottom, x minus 5. Okay. And then second window, and I'm going to change my independent variable to ask. Okay. So now when I go to the table, second graph, there should be nothing. Now there's stuff there just because I've had crap in here. Okay, but yours should be clear. All right. So I'm going to start with 4.9, and it's going to automatically populate the value. Okay. And then I'll do 4.99. Okay. And then 4.999. So you notice it just changes, right? So my value just keeps changing and changing. You're going to see all of them. Mine just shows me one. Okay. And then likewise, 5.001, 5.01, whoops, and then 5.1. Okay, what happens when you put 5 in? It says error. Okay, why is the error happening? It would cause a 0 in the denominator. Okay. So looking at this, all right, as I got closer, I noticed I was at 0.11.16666 on both sides. Okay. All right. What are we getting really close to? Yeah, that 0.166. So we would say the value of this limit is 0.16 repeating. Do you happen to know what fraction that is? It's 1/6, isn't it? Somebody double check me. Yep. All right. So we're getting really close to 1/6. Okay. I wouldn't expect you to know that. It would be a decimal approximation. Okay. So we're just going to put those values in. We get error when it gets right here at 5 because we know it's undefined. But that's how the table works, okay? And ask is a really great feature, all right, in that regard. So it'll just save you a bunch of work instead of having to plug it in every time. I mean, could you just go to the home screen and plug in those values? Sure, all right? But it will do it for you in the table, which is nice, all right? So what do you think about that? Not so bad? All right, so here's the dill pickle. Let's get into the meat and potatoes, all right? Graphs, it's a visual. It's right there. I can see it. Tables, same thing. It's a visual. Right there, I can see it. So when we talk about methods for finding limits, there are 3 main ones. The first is to graph it, which is what we did first. All right, it's very visual. The second one is a table. Again, very visual. The last method that we get to, or what we refer to as algebraic properties and algebraic manipulation. Right? These are going to be the ones that are in your non-calculator sections. Okay? Algebraic properties and manipulation. Okay? So what I want to do is just kind of walk through some of that for you. A lot of times they will make limits very kind of general. All right? They'll give you some general values and then ask you to come up with some limits when you don't know a function. And that's where these properties are important. So let's just talk about them for a second. Okay? When we talk about the limit of a constant function, all right, a constant function would be y equals 4, y equals 7, y equals negative 21.3. All right? So a constant function, right? So a constant function would look something like this. All right? It would be the line y equals k, whatever that k value is. Does it matter what x value I approach when it comes to that function? Okay, it's going to matter, right? But does the y value ever change? No. So if I take the limit of a constant, it is that constant. It does not matter what I approach, it will be that constant. Okay, so the limit as x approaches c, so if c is right here, the y value we'd be getting close to is k because it's constant. All right, the y value never changes, so that limit is going to always be the same. Okay, let's think about the identity function. All right, the identity function is y equals x. All right, so if we were to graph that, y equals x. Okay. If we think about approaching some x value c, what would the y value be? If y equals x. Okay. What if c was 3? It would be c. It'd be whatever I'm approaching. Okay. So the limit as x approaches c of the identity of x itself, okay, is that value we're approaching. And that's really important. This leads me to what I refer to as direct substitution. Okay. If I've got a function there and I know what x value I'm getting close to, I plug that close to number in there. Okay, because that's the identity. Whatever's there is what we will get. Okay. Now, the good news is, right, is that these 3 down here are pretty awesome because they're all match, right? If direct substitution works, if I'm adding 2 different things together, guess what? It's the same thing. I'm just going to plug in whatever we're approaching. So these are all going to be the same. So if I take the limit as x approaches c of f of x plus g of x, and one way to think about that would be like x plus 7. Okay? I can separate it. All right? It's 2 separate limits. The limit is x approaches c of f of x plus the limit as x approaches c of g of x, okay? The good news, it's true for all operations. okay? So we can add limits, we can subtract limits, we can multiply limits, all right, and we can divide them. Nothing about that changes. Right. All right, and that leaves me to two last ones. Okay, two last properties, algebraic properties for limits. You're going to find that the algebraic properties for limits transcend the algebraic properties for derivatives and for integrals. Like it all kind of works together. They're not all identical, but they do transcend kind of the same basic principle. All right. So if we talk about a constant multiple, that just means I'm taking a function and I'm multiplying it by something. All right. So think y equals 3x. Okay, so if I have the function y equals 3x, it is still that identity function. What's the only thing that's changed? The slope. Okay, the slope is all that's changing. So if I go to c, it's not just x now, it's 3 of it. Okay, so the constant multiple rule says this: if I take the limit as x approaches c of k times some constant times f of x, it's just the identity function limit multiplied by that constant. Okay, so we can just pull it out to the front. All right, again, just think direct substitution. And we're going to plug stuff in. All right, and the last one's a little bit more confusing. It's a power rule, power meaning an exponent. So if we take the limit as x approaches c of f of x raised to some power n, all right, that's the same thing as raising the whole limit to that power. Limit as x approaches c of f of x to that power. Okay, again, it's direct substitution. All right, we can take that independent limit and then raise it to that power. Now, I put a little caveat here for you just so you can have this in your notes, all right, instead of us writing it, all right? If either one of those limits does not exist, okay, so let's say we're adding two things together, we're multiplying two things together. If one of them does not exist, it does not automatically mean that the entire limit doesn't exist. It just means we can't do it using properties, okay? So there might be another way to get there, but we just can't do it using the properties that we know. Okay, so let's put those properties to use. Example 7 is a really good one. I'm going to do one of them with you, and then I'll let you try the other ones. Okay, I'll let you try the other ones. So notice they give me some information. They tell me that the limit as x approaches 3 of f of x is 5, and the limit as x approaches 3 of g is 4. Okay, we don't know what f and g are, but we do know values that they're approaching. Okay, so if I look at that first one, actually, I'm going to do the second one with you, and I'm going to let you do the other two. All right, so let's look at B. So I want the limit as x approaches 3 of g of x divided by f of x minus x squared plus 5. What this really means is that I can split all of that apart. I can take the limit as x approaches 3 of g of x. I can divide it by the limit as x approaches 3 of f of x minus the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 5. Now, you don't necessarily have to write all that out, but that's what it's saying, okay? That's what it's saying. And the good news is we can use what we know about properties to get all those values, okay? They gave me the first two, which was really nice, okay? They gave me those first two. So what was the limit as x approached 3 for g? It was 4. And what was the limit as x approached 3 of f? It was 5, okay? On the next one, we're just going to plug it in, okay? So my function is x squared, so that's 3, and I'm going to square it. And then what's the limit as x approaches 3 of a constant of 5? Just 5, all right? And then we would do the arithmetic. 3 squared plus 5, that would be what, 14? So I have 4/5 plus 14. Let's see, 14 would be 70. 14 times 5 would be 70. 0 carry 2. Yep. So I would get 74/5 is the value of that limit. Okay. So just using what we know, direct substitution, plugging things in. You try A and C real fast. You don't have to do all that middle work. You can go straight to the new numbers. All right. The purple stuff. Somebody's birthing a baby over there. I'm not really sure what's happening. I think they're reviewing. I think they have a test tomorrow. I have no idea. Gorilla noises, maybe. I'm not sure. Yikes. Bless them. Highly competitive. I'm going to go with highly competitive. And his group must not be winning. It's one of the nice things about having metal walls. You get a lot of information between the classrooms. So just so you know, when we act crazy, they hear it too. All right, what'd you get for the first one? As x approaches c of 7 times f of x. 35. It's just 7 times 5, which would be 35. Good. Okay, so just 7 times 5, which would be 35. Okay, and let's look at this one. Notice it says from the right. Okay, from the right. We have limits here that exist from both directions. So guess what it is from the right? The same thing. Okay, so we just have to understand that that's what they told me. So when we plug this one in, f of x divided by 11, so that would be 5 over 11, times the square root of g of x, so the square root of 4. So 10 over 11. Okay. All right. Question about those. So that's when they don't give you the functions, but they give you values for the limits. We can use properties that way. All right. Same thing holds true for these last two. All right. Direct substitution. Go. See what you can do. Can you evaluate those limits? Right. Okay, I can promise you these will all be non-calculator. Okay, so they're going to expect you to do your arithmetic. It will all be on your non-calculator section, especially with fractions. Get used to that. They're going to expect you to operate with fractions. Okay, so without a calculator, so we'll do a lot of that. What is this Van Dyke shirt you have on, Carly? There's a Teletubby on there. Is this the one you drew, Marshall? Okay. Okay. Okay, check with your table group partner, see if they agree with what you got. Woomer, we still turning over a new leaf? Yeah? Okay. All right, just checking. You're going to be the Jawak of this semester, this year. Huh? Well, no, but he worked he gradually made improve. That didn't come out right. That's not what I meant. He was I've got one more in me. Like when I sent out that their scores were in and everybody had made 4s and 5s, he was like, I knew I had one more in me. So, bless him. He improved every year. Sorry, didn't mean to insult you there. Or insult Jawak. I really insulted Jawak. He goes to school, I think next week they move in. Good old Tennessee Tech.
That makes sense.
My stomping grounds. I was like, how are you going to fit in the bed? There's no way you fit in the beds in the dorms. But, okay, he would need extra long. Yeah. Yeah. I think it's cool, though, that they did that. All right, so on the first one, we're just going to plug in the 2. All right, direct substitution. So 2 squared plus 2 times 2 plus 4 over 2 plus 2 should give me 12 over 4, which is 3. Okay? Likewise, we do the same thing for the second one. We just plug in direct substitution. They give me a function. We plug in that x value. So I get the cube root of 2 times 3 squared minus 10. Just do your arithmetic right. All right, 18 minus 10. So the cube root of 8, which is 2. Okay? So as long as we plug in and life is good, fantastic. All right? But we all know that's not how the world works, okay? Never has, never will. There's always the exception to the rule, which is what we seem to live and deal with, okay? So let's talk about algebraic strategies for evaluating limits. When direct substitution produces an indeterminate form. Now, that's a new word for you. Indeterminate form means it's giving me a 0 over 0, okay? Not only does my paper explode, it's a conundrum. Okay, we just don't want 0 over 0. Right. There are 2 basic strategies that we use. The first one is to factor and reduce. Okay, but before you start trying to factor, double check. All right, that direct substitution actually gives you 0 over 0. So if I plug in 2, I just start with the denominator. Okay, if I plug in 2 cubed minus 8, that indeed gives me 0. All right. 2 squared minus 4 gives me 0. So I do need to factor and reduce. One of the other ones we did a few minutes ago, we could have factored and reduced it, okay? But we didn't need to, right? Because we didn't have it in indeterminate form. So for this one, keep that limit when you factor, all right? So notation is going to be the biggest thing. You drop a limit when you substitute, okay? So right now I'm not substituting. How would I factor x squared minus 4? Good. X plus 2, x minus 2. All right. So that's how we factor the numerator. Let's factor the denominator. That's a difference of cubes. It's been a hot minute since we've done that. Okay. Remember, the first parenthesis is the cube root of both those pieces. So that would be x and 2. When you factor a cube, it gives you a binomial and a trinomial. Remember, we use that phrase SOAP. Okay. Same sign, opposite sign, always positive. Okay, so SOAP when it comes to cubes. Now, we square the first term of the first parenthesis, which was x squared. We square the last term, which is 4, and then we multiply the 2 terms together. So 2 times x would be 2x, and that's how we factor. Right? Why is that important? Well, is there something that will reduce from numerator to denominator? Yep, my x minus 2's. Okay? Once I do that, I can now substitute. Okay? So when we substitute, we're going to drop the limit. So that gives me 2 plus 2 over 2 squared plus 2 times 2 plus 4, which is 4 over 12 or 1/3. Okay? So factor and reduce. You're going to have to remember all your factoring techniques. Okay? Remember, for cubes, it's SOAP. Same, opposite, always positive. Okay? Y'all try the one next to it. Try the one next to it. Okay, if I plug in 0, does it give me indeterminate, 0 over 0? It does. So we need to factor. So let's look at the numerator. What could I pull out of both parts of that numerator? X squared, and that leaves me 5x plus 8. In the denominator, what are we going to pull out? X squared, and that leaves me 3x squared minus 16. I'm going to reduce those x squares and try plugging in 0 again. Okay? If I plug in 0 this time, 5 times 0 plus 8, notice I dropped the limit. 3 times 0 squared minus 16 gives me 8 over negative 16, or negative 1/2. Okay? And that is the value of my limit. In other words, if I took that whole big function and I put it in the calculator and we looked at what happened as we got close to 0, my x's would be getting, my y's would be getting closer to negative 1/2. Okay? All right, so let's look at this next one together. All right? This is the one that most people tend to have the most problem with because it's a complex fraction. All right? There's just a lot of crap we have to remember algebraically. Okay? The algebra in this problem is 1,000 times worse than the calculus. The calculus is just substitution. All right? But the algebra is brutal. Okay? So when I look at this one, obviously if I plug in 0, 1 over 0 plus 4 is a fourth minus a fourth, which is 0. 0 on the bottom, it is indeed indeterminate. Okay? So here's what we're going to do. We're going to keep this limit because I got to do a bunch of algebra. The limit as x approaches 0. All right? My denominator of just an x, he's okay. All right? Like, that's not really an issue right now this minute. But what is an issue is that I have two fractions on the top. Okay? Which means I need a common denominator. That common denominator is going to be the product of both the denominators I already have. So 4 times x plus 4. Okay? 4 times x plus 4. So let's take a look at each fraction. In the original fraction, the first one, I had the x plus 4. What was I missing? in the new denominator. Yep, I was missing the 4, so I'm going to multiply it by the 1. 4 times 1 is 4. Okay. In the second one, I had the 4, but I was missing the x plus 4. So I'm going to multiply that 1 by x plus 4. Right. Now, I'm still working, so I'm going to keep this limit. I'm not ready to substitute yet. Okay. So on the top, my new denominator is 4 times x plus 4. My numerator is now 4 minus x minus 4, and I'm still dividing the whole thing by x. All right, so I'm just doing a lot of algebra right here. Okay. Going to keep the limit because I have not reduced everything yet. All right. It's going to leave me with a fraction divided by x. What's the fraction going to be out of that whole big numerator? What's going to happen to the 4's on top? They're going to cancel out. And so I'm going to get a negative x over 4 times x plus 4. I'm going to divide that by x, which means I'm actually going to multiply by 1 over x, right? So we keep change flip when we do fraction arithmetic. Okay. Now is there something that's going to reduce out? I love that they write your name on those shirts on the arm. Okay. So does everybody see what I did there? I kind of put 2 steps together, right? I simplified the big numerator. Instead of division, I changed it to multiply, and I did the reciprocal. Okay, so keep, change, flip. Now, these x's are going to cancel out. So this leaves me with the limit as x approaches 0 of negative 1 over 4 times x plus 4. Okay, so that's the algebra. And it's gross. All right, you're going to need to practice some of these. All right, you will see it on your first quiz on Friday. Hint, hint, wink, wink, nudge, nudge. Okay, so now we'll plug in 0, and that gives me, I drop the limit, negative 1 times 4, negative 4 divided by 4 times 0 plus 4, or negative 1/16. Okay, again, you just got to practice that algebra. All right, what questions do you have? I don't want to move on until we're sure about this algebra. All right, so the next thing still happens that I get something indeterminate, but this time there's a big nasty radical up in there, okay? So what we're going to do to simplify these is we're going to rationalize with conjugates. Now, think back to complex numbers. If I had 2 plus 4i, what was the conjugate? Big word. That's all the way back to freshman year. 2 minus 4i. We switch the sign in the middle, okay? So when we have a big radical, it doesn't matter if it's in the numerator or the denominator, okay? What we're going to do is we're going to multiply by the conjugate over the conjugate, all right? So the conjugate of the radical. Because if I plug 0 into this one, obviously I'm still going to get something indeterminate. So this is still indeterminate. So still 0 over 0, okay? So what I'm going to do is I'm going to multiply. My conjugate would be square root of x plus 1 and then plus 1 over square root of x plus 1 plus 1. Okay, so that would be the conjugate right there. Okay, conjugates are important because they're going to, one, get rid of my radical, right, which is what we want. Right. So I'm going to keep that limit as x approaches 0. Okay, so in the numerator, if I take square root of x plus 1 times square root of x plus 1, I distribute, what would I get? The radical times the radical goes away, so I would get x plus 1, right? Because it's a conjugate, the middle term goes away. Typically, when we multiply binomials, we get a middle term, but that's not going to happen because one's positive and one's negative. So I'm just going to get this other term. What's negative 1 times 1? Negative 1. Now, wherever the radical is not in the original, don't multiply it out, okay? Leave it x times square root of x plus 1 plus 1. That's in factored form, and we want to leave it, okay? And I think you'll see why here in just a second. If I look at that new numerator, what's going to happen? Yeah, the ones are for sure gone. And it leaves me x over x times the square root of x plus 1 and then a plus 1. All right? Now can I reduce numerator to denominator? Who's going to disappear? The x's. Can't leave that top empty, so it's going to leave me with a 1. Okay? And now we can substitute. All right? 1 over the square root of 0 plus 1 plus 1, which would just be 1/2. Okay? So that's a conjugate. You can use that whether it's in the numerator or the denominator. Okay? It will have the same effect. Okay. Gets rid of that radical so that we can mess with things a little bit nicer. Okay? I want to do one more of those with some just weird looking notation in there. All right? But it works the same way, which is nice. Okay? It's going to work exactly the same way. Aren't you glad I didn't leave y'all the video for this? Yeah, I was going to leave you a video for this. And by the way, y'all can thank Gavin. He's the one who's like, well, let's do trig equations. Great idea. That's what we should have done. Okay, so appreciate that. I always like it when y'all have good ideas. It helps me. Okay, here we go. Let's look at this one. All right. So there's some symbols here that you probably haven't seen. Does anybody know what that triangle means or what Greek letter it is? Delta. Yeah, it's delta x, okay? It stands for the change in x, and that'll make more sense next chapter, okay? But it stands for the change in x. But notice we're talking about where the change in x approaches 0. In other words, if I put a 0 in everywhere that weird symbol's at, that gives me the square root of 3x minus the square root of 3x, which is 0, over 0. So it is indeterminate, okay? Because there are radicals here, we're going to multiply by a conjugate. Right? So I'm going to have the square root of 3x plus delta x, that's just a triangle. Instead of minus, I'm going to have plus square root of 3x. And we're going to do that top and bottom. Okay? So square root of 3x plus delta x plus square root of 3x. What I'm doing is multiplying by 1. All right? And as long as I multiply by 1, I don't change the value. Okay? I like to refer to it as the well-chosen one, like a superhero. All right, so now we're just going to do a bunch of algebra. I'm going to keep my limit because I'm still working. Delta x approaches 0. On the top, all right, we're just going to multiply those two things. So each square root is basically going to disappear. So I have 3x plus delta x. I keep the minus, and square root of 3x times square root of 3x is 3x. The numerator, I'm not going to distribute. Okay, because there wasn't, the denominator I'm not going to distribute because there was not a radical in it to start. So that's going to be my factored piece, which is going to be square root of 3x plus delta x plus square root of 3x. Okay. Looking at that numerator now, what's going away? The 3x's, yep. So it's going to leave me the limit as delta x approaches 0 of square root of x over square root of x times the square root of 3x plus delta x plus the square root of 3x. Right? Because that denominator is now factored, does it reduce? Okay, so I'm going to lose the delta x's that were out there in front. Can't leave the numerator empty, so I'm going to put a 1 there. And now I'm ready to substitute. Okay? And so I'm going to get 1 over the square root of 3x, delta x is 0, plus the square root of 3x. Now, radical arithmetic here. What's the square root of 3x plus the square root of 3x? Do we add under radicals? Oh, I told you, it's the algebra. Okay. We don't. We multiply under radicals, but we do not add. So that would just be like terms. I have 2 square roots of 3x. Yes, I know. I still have an x in my answer, but that's okay. X was not my variable. Delta x was my variable in that one. Okay. So that one's kind of an extension of some things to come. All right. Where we'll get algebraic answers. All right. Woo! That was a lot, okay? That was a lot of algebra right there for you, okay? So your lesson practice tonight, there was a worksheet back there. It's a practice worksheet, 1, 4 through 6, so that's there. And then on page 70, number 9, number 13, 15, 25, 26, 27, 28, and 29, okay? I'd go in and especially look at the ones that have rationalization in them or have like complex fractions in them, okay, or any kind of factoring that you aren't sure you understand, okay? All of the answer keys are posted already, okay, so you'll be able to double check those, right? And then your wrap up today, you can do that on a sticky note. I'd use a bigger one, okay, out of there. But it says to construct a table to find that limit. I want to see your table. Okay, so I want to see your table. Okay, so do it on a Post-it. Turn it in. Be sure your name's on it. Although at this point I could probably recognize the handwriting, but let's don't chance it.
I think you could.
Yeah. After a semester, I'm pretty good at that.